Hello YouTube. I'm going to show you guys how long it would take if you fell through the earth. Now, imagine there was a hole in the earth. I know I didn't put it in the exact middle. I'm sorry. But imagine it was right at the poles, right? So, here's you. Okay. Now, here's the center. Again, imagine this is a little more to the left. And here's the radius r. So, if you imagine the radius, as you're falling, the radius decreases. Till you get here, the radius is 0. And if you keep going, we can assume the radius is actually negative. So if you're here, the distance away from the center would be the radius. And if you're here, the distance away would be the negative radius. Keep that in mind for later. Now, how do we figure out how fast, how do we figure out how long it'll take? Well, we have to figure out how fast we'll be going. Well, we won't be going at constant speed. Also, we're going to assume there's no air resistance. But we'll be accelerating and decelerating. So we need an equation. Now, we can use Newton's second law, F equals ma. And the gravitational law, the force of gravity, is equal to, in this case, we'll make it negative because it's pulling away from the center spot. So mass, so your mass times the mass of the Earth times the gravitational constant over r squared. Okay, I actually have the values written out here. This is the density of the Earth, average density. This is the mass of the Earth. This is the radius of the Earth, and this is the gravitational constant. So we have this value. Now, off to the side, we know density is equal to mass over volume. Hopefully. Sorry. We're going to assume the Earth is a perfect sphere of equal density. And the volume of the Earth, since it's a sphere, is equal to 4/3 pi r cubed. And so density is a constant if it's a perfect sphere. Density is constant. So the mass of the Earth, the reason we need to know this is if you're falling down, when your radius decreases, you make, imagine a smaller Earth as you fall down, because the stuff up here is pulling away from you in all directions, so it just cancels out. So once you've passed the line on here, once the further down you go, everything above you from the top of the Earth can be ignored. So it's like the Earth is shrinking, and it's like instead of falling, it's like the Earth is just shrinking, and so that's how, since we're considering it a perfect sphere, that's why we can do that. So that means if the volume will be changing, the mass will also be changing, because if there's less of the sphere, then obviously it'll weigh less. So the mass of the Earth at any given time would be equal to the density, which is a constant, times the volume, which is equal to 4/3 pi radius of the Earth cubed. Okay, and well, let's just do a lowercase r. So the radius is always going to be changing if you're falling. So we can plug this in here. So the force of gravity is equal to your negative mass, the mass of the actual person falling, times mass of Earth, which we did up here. So dE 4/3 pi r cubed over r squared. And this cancels out with the r cubed to get this. Now, m density 4/3 pi. Oh, I forgot g. And -1 these are all constants except for r. So I'm just going to say k is equal to not negative, sorry, I'm keeping the negative, is equal to mdE 4/3 pi g. So now we can rewrite it as Fg equal to negative kr. Now, if you fall on the earth, the gravity, because as the radius decreases, then the attraction towards the center will decrease. So once you get to 0, there'll be no force, but you'll already be moving, so you'll go past it, and then you'll be going really fast, and then the acceleration will be pulling towards the center, so it'll be pulling away from you while you're going this way. So it'll be slowing you down until you reach the top, and then you'll go back up here, and you'll just go in a constant wave back and forth. Now, motion where you just keep going back and forth is called oscillatory motion. Now, if you know the function sine of x, here pretend it's a graph. Well, this is not sine of x, but it goes on forever. So that was really bad arrows. So it just goes in a continuous wave forever. So it just keeps going back to the same points over and over. So the distance away, the radius, the force is dependent on that. Now, I specifically chose K, so if people who know physics would recognize that I'm basically doing the same thing that you would do for simple harmonic motion with a spring. So this force is equal to ma, Newton's second law, and acceleration is the second derivative of the radius with respect to time. So negative k over m times r is equal to the second derivative, and you could solve the differential equation, but it requires a lot of math. But and there's multiple solutions, and so the standard oscillatory motion, if you get force equal negative k, which k is a constant, then you'll get the radius at any given time is equal to the amplitude times cosine of the square root of k over m, which is also equal to the angular frequency w times t. Oh, plus the phase constant. And amplitude and phase constant we don't know. Well, we do know that we're setting initial conditions if you're starting from rest. So r prime of 0 is equal to 0. So your speed at the very beginning is 0, and your position is going to be the radius of the Earth. Like your initial position is going to be the radius of Earth, and your initial speed is 0. So knowing that, we take the derivative of the radius, r prime of t, equal to, and then I'll just use w from now on. So it'd be negative w a sine of wt plus phase. And so we make 0 when we plug in 0. So 0 equals, and you plug in 0 and you can get rid of that. So 0 equals sine of the phase constant. And that means the phase constant can equal 0, pi, 2 pi, ... So any multiple of pi. We're going to choose 0 because if you start with the cosine function as our regular function, if you actually graph a cosine function, it starts at 1 and then decreases as t increases, and then so it immediately decreases from time equals 0, and that's what you'll be doing here because you'll start going down. So you actually want the phase constant to be 0. And so find the amplitude, we also will use r of 0 is equal to radius of the Earth. I guess I'll write it down. So, oh no. So if we're saying the whatchamacallit, the radius of Earth is when r is 0, a cosine of 0 plus the phase constant, which is also 0. and cosine of 0 is 1, so amplitude is the radius of the Earth. So now we can rewrite it. The radius with respect to the radius at any given time is equal to the initial radius of the Earth times the cosine of the square root, and we'll plug in k, m dE 4/3 pi g. Oh, and the m's cancel out because you divide k over m. T. Okay. Now, we are trying to find when this is equal to negative RE, right? So you go down here. So let me get a new page. I'm going to keep that up here just to show. So our radius is going to be negative the radius of the Earth. So that way we can find the distance from the top to the bottom, which is the diameter. So we're going to make that equal to RE cosine of the square root of d of the Earth 4/3 pi g t. Okay, now we divide RE by RB, so the cosine would be equal to -1. And if you remember your unit circle, the only place on the unit circle, only place on the unit circle, if this is 1 and this is 1 on a square. So if you're thinking on a graph, like on a grid, so this would be 1, 1, this would be 0, 1, this would be -1, 1, etc. On a circle, the only spot where x can be equal to -1, because if it's here, it's less than -1, and if it's here, it's positive. So right here, and we figure out how many degrees that is and convert to radians. So that is 180 degrees, but in radians, it is pi radians. So -1 is equal to the cosine, which is the x value in the unit circle. So basically we're saying pi is equal to what's in here. So pi is equal to the square root of dE times 4/3 pi g times t. So that means the time is equal to pi over square root of the density of the Earth times 4/3 pi times the gravitational constant. So let me pull out a calculator and let's do that. So let me do the square root of, so I'll pull out my numbers here. Density of Earth is 5513.26. Make sure you're using the correct measurements: kilograms, meters, seconds, and yeah, so that's density. 26 times 4/3 times pi times 6.67408 times 10 to the -11. Okay, so now we have this number, and that's everything in here. And so I'm going to raise it to the power of -1. So that way I'll raise it to the power of -1 and then multiply it by pi, because this calculator's, you can't really put this on the denominator. So to the -1 and then multiply it by pi. So our time in seconds is equal to 2,530.495 8 seconds, which is equal to 42 minutes, and we'll subtract 42 by 60. 42 minutes, 10.5 seconds. So, there you have it. If you fell through the earth, assuming it's perfectly spherical, it would take about 42 minutes and 10.5 seconds. Now, the real value, because you have to take into account the different densities of each core versus the actual value, and the Earth isn't a perfect sphere, so the gravity would be changing, and it's actually about 38 minutes, but this is a close estimate, so let's say 42 minus over 38. So we got a 10% error. So we got about a 10.5% error, which is it's not amazing, but the Earth is not that spherical. But yeah, if you fell down the Earth, also, you would have to fall down from the poles, because since the Earth is rotating, if you fell down from somewhere else on the Earth, so imagine this crack is like that hole right here, the hole right here. So if you started falling down, so you were originally rotating with the Earth, but if you fall down, then the Earth starts rotating and you will hit the wall. So like they've done an experiment where they had like a mile-long shaft in a mine, and they threw a bowling ball down, and it just hit the wall, and it never hit the bottom. They don't know where it went. So anyways, thank you guys for watching. Sorry for making the video so long, but that is how long it would take if you fell through the Earth.